Hello, everyone. Today we'll be talking about Group 2 elements in the periodic table, otherwise known as the alkaline earth metals. So the general properties of the alkaline earth metals is they're good reducing agents, and their reducing ability increases with the atomic radius size. So as we're moving down the row, reducibility will increase. And they tend to form +2 ions to achieve noble gas configurations, so they will lose 2 of their valence electrons. They generally react with acids to generate hydrogen gas, and they have a shiny metallic luster. In their elemental forms, they're good conductors of heat and electricity. They are malleable and ductile, which means they can be pulled into long wires or molded into shapes. And they're similar, have metallic properties of the alkali metals and the transition metals.
So the beryllium is the first element in the group 2 elements. The weight of it is about 9, and the atomic radius of it is about 112 pm. So we will pay more attention to the atomic radius in this presentation because you may see that as the elements go down, the atomic radius will increase. You may see that in the later introduction. So after that, the melting point is about 1300 degrees and the boiling point is about 2500 degrees. And the crystal structure of the beryllium is the simple hexagonal structure. So you may see the simple hexagonal crystal structure from this picture. So you may see the A bond and B bond is equal to each other, but the C bond not equal to each other, and the angle between the AB bond is about 120 degrees. After introducing some basic property of the beryllium, we may see the beryllium in the industrial or the experiment condition. The first question is that how do we get the pure beryllium? So normally people isolate the beryllium from the emerald. So they may have about 5 steps to get the pure beryllium. The first step is we will use the emerald to get the sodium beryllium fluoride. Then we will use the sodium beryllium fluoride. We will change them to the beryllium hydroxide. Then we will use the beryllium hydroxide to directly react with the sodium hydrofluoride to get the beryllium fluoride. Then we can use the magnesium to reduce the beryllium fluoride to get the pure beryllium. So besides the industrial properties, we may also realize the all beryllium compounds are toxic and they may cause the cancer for humans. So from the table over here, we may see that lots of beryllium compounds have very low LD50 value, although they have a bit higher value than the KCN, sodium azide, some mercury compound, something like that, but they're still very, very dangerous. And they may also combine the proton compound in humans' lung cells. So it means that they may combine the proton and cause the cancer in humans' body. Then we will see the applications of the beryllium in the industrial or in our daily life. So there are more than 70% of the alloys may combine the beryllium, especially the copper alloy. So the advantage of these kinds of alloys is they have lower density and higher melting point. Then it will be resistant to the oxidation and other kinds of good advantage. Then besides that, the beryllium oxide also can stay in the high temperature or the corrosive environment, and it will protect some equipment in some kind of harsh condition. Then the beryllium can also used for the organomagnetic compound. So in this graph, we may see the reaction how to synthesize some beryllium or complex. So this complex may used for the catalytic made for the catalyst in the organic reactions or kind of other things such as material science or something like that.
The next element we're talking about is magnesium. Magnesium has the atomic number 12, which means it has 12 protons in its nucleus. It has a molar mass of 24.305 grams per mole. The atomic radius is 1.6 angstroms. The boiling point is 1,105 degrees Celsius. The melting point is 649 degrees Celsius. And the density is 1.738 grams per centimeter cube. The crystal structure of magnesium is hexagonal closed packed, which is shown in this orange image on the right. It has an ionization energy of 738 kilojoules per mole, an electron affinity of negative 40 kilojoules per mole. And once magnesium is the elemental form, it is silvery and shiny like this. How magnesium is found in industry, it is not naturally occurring in its elemental form. It is generally found in minerals such as magnesium carbonate, which requires mining. Once magnesium carbonate is mined, its extracted minerals are treated at high temps to form magnesium oxide. The magnesium oxide is then mixed with iron, allowed and heated to high temperatures. Finally, it is mixed with a zinc alloy and refined to get a desired product. And to get magnesium solid, it can be reduced using general electric chemistry, as in this figure shown on the right. Magnesium has a wide variety of uses in reactivity. It's used to create the famous Grignard reagent, which gives this carbon in this diagram a negative charge and becomes nucleophilic. Its electropositive magnesium has this generally has a lone pair represented on this carbon with a negative charge, making it more nucleophilic to attack electrophiles. It's used as a cofactor in the production of ATP and the synthesis of DNA and RNA. A cofactor will guide enzymes or reactants into proper orientation in biological systems to allow proper binding to occur and the reaction to progress. It also helps regulate heart rhythm and electrolyte balance in biological organisms, and is taken as an over-the-counter supplement. And it is most similar to zinc, because zinc also forms 2+ ions, and their atomic radiuses are quite similar, with zinc being 1.42 angstroms. Next element we're going to talk about is calcium. Calcium being one rung lower on our alkaline earth metal ladder. It has an atomic number of 20. The molar mass is 40.078 grams per mole. The atomic radii is 1.97 angstroms. The boiling point is 1,494 degrees Celsius. The melting point is 839 degrees Celsius. And its density is 1.55 grams per centimeter cubed. The ionization energy is 590 kilojoules per mole. The electron affinity is negative 30 kilojoules per mole. And the crystal structure is face-centered cubic, or FCC, which is shown in this top picture right here, showing that how the cubes stack one another three-dimensionally. And fun fact about calcium is it is the 8th most abundant element in Earth's crust. Calcium is used in industry. It is also not found naturally in its elemental form. It is primarily found in limestone, which has the formula CaCO3, or calcium carbonate. The calcium carbonate undergoes decomposition. The calcium oxide releases carbon dioxide. The calcium oxide is then hydrated with water to form calcium hydroxide. The soluble calcium hydroxide is then plated similar to how we saw magnesium be plated with electrodes. And calcium is most similar to potassium, as they both react aggressively with water in the similar atomic radius of calcium and potassium, where potassium's is 2.27 angstroms. And here we can see a calcium processing plant in this picture. Now, the reactions calcium undergoes, it reacts readily with the halogens to form salt halides like calcium chloride, and it reacts, it's one of the only alkaline earth metals to react with nitrogen, where it forms calcium nitride. And it also follows the trend of most of our alkaline earth metals, where it releases hydrogen gas when reacting with acid. Calcium is a necessary component in the formation of our bones and our teeth, and it is a critical cofactor in blood clotting, nerve signaling, and many enzymes require them to function. It is also a secondary messenger to the pancreas and releases insulin when introduced to the bloodstream. It is required for muscle contraction, where it allows actin and myosin fibers to bind so we can bend our muscles in our daily lives. And it is a fun fact, is named by Sir Humphrey Davy in 1808 where it was isolated in electrolysis in a crude mixture of lime and mercuric acid.
So the next element is called strontium. The strontium was found in a small town of Scotland in about 18th centuries. This small town is called Strontium. So that's why this element is called strontium. And strontium has the atomic weight of 87.62 and radius of 250 picometer. And the boiling point is 1382 degrees Celsius and melting point of 777 degrees Celsius. And the density of this element is about 2.64 gram per cubic centimeter. And it has a face-centered cubic crystal structure. And we can see that the strontium element is a kind of yellow, and the strontium oxide is a kind of white powder. So it is a little bit different with other element in this group. And there's no pure strontium element in nature. There are two different type of mineral ore in nature can be found called celestine and strontianite. So the celestine is strontium sulfate, and strontianite is strontium carbonate. And in our industry, there are two different ways to synthesize pure strontium element. The first way is use celestine reacts with carbon to get strontium sulfide, and strontium sulfur in oxygen environment to get strontianite, and strontianite can react with alumina in very high temperature and to get pure strontium element and alumina oxide and carbon monoxide. Another method is just electrolysis method. We use strontianite reacts with acid. For example, the hydrochloric acid, and also we can use the celestine reacts with carbon to get strontium sulfur, and strontium sulfur reacts with hydrochloric acid to get strontium chloride, and strontium chloride we use the electrolysis method to get pure strontium, but this method is really energy cost. So, but this method can get very pure strontium element. So in some laboratory we use the second method, but mostly we use the first method. There are several applications for strontium. First, it can be absorbed by our bones. Therefore, people can use strontium to identify human remains in battlefield in burial site. And strontium 90 is a really radioactive isotope. It can be used as beta ray radioactive source, but it is very harmful to human body. And third, a glass castle ray tube inside of color televisions. It can be called CRT. So this tube can use as protecting against X-ray radiation. And fourth way is strontium 97. It also can be absorbed by bone. And also it is a radiation detector to identify anomalies. And the fifth, there are several research tendencies for strontium. First is the strontium titanium oxide. It has an extremely higher radioactive index and higher optic color than diamond. So there are some optical research can be used in strontium titanium oxide. And strontium can be used to create some ferrite magnets. For example, strontium ferrite oxide and strontium ferrocobalt oxide. Third, strontium oxide can be used to prove the gross quality of So the next element is called barium. Barium was found by an English chemist called Humphrey Davy. His another name is the father of inorganic chemistry. Barium has an atomic weight of 137.327, and the atomic radius is 222. The boiling point of barium is 1897 degrees Celsius, and melting point of 727 degrees Celsius. The density of this element is 3.51 gram per cubic centimeter. It has a body center cubic crystal structure, and this is a barium crystal. It has a black and or silver color. Barium is really reactive, so there's no pure barium element can be found in nature. There are two types of mineral ore which contain barium in nature. The first is called barite, it's barium sulfate, and another is mithrite, it's barium carbonate. There are two ways to synthesize pure elements. The first is use barium sulfate reacts with carbon to produce barium sulfur, and barium sulfur reacts with alumina can be produced barium element. But this way we need to remove some impurities in the final. And another method is electrolysis method. We use barium sulfur to react with sodium carbonate to get barium carbonate participation. And barium carbonate react with hydrochloric acid to get barium chloride. And our old friend barium chloride can react with electrolysis, can be used as electrolysis method to get pure barium. This way can be used in our lab to get pure barium. There are several applications for barium. The first is water-soluble barium compound are toxic, but the low concentration water-soluble barium compound can be used as muscle stimulant. And another is barium alloy can be used as barium alloy because barium alloy has a high strength. Third is called barium enema, and barium enema is not another name called barium enema is called barium meal. It can be used to cure some stomach disease. And the fourth is barium peroxide, can be used as some catalyst in thermite for welding reels. The fifth is very similar with strontium. They can be used as producing ferrite magnets.
So let's see the last element in the group 2 elements, the rhodium. The rhodium, the weight of it is about 226, and the atomic radius of it is about 283 pm. So we may say like it has the largest atomic radius in this group. The melting point of it is very low. It's only about 730 degrees, and the boiling point is only about 870 degrees. But it still has the largest density. It is about 5 grams per cubic centimeter. And the crystal structure of it is the body-centered cubic. So from the graph, we may see that the body-centered cubic has 3 equal bonds, A bond, B bond, C bond. They are equal to each other, and the angle between these bonds is 90 degrees. Then we may see that how to get the pure rhodium in the industry or the experiment. So the rhodium is a kind of trace element on the Earth. So normally in the real life, people may extract the pure rhodium from the nuclear fuel rods, or people may also get the pure rhodium from the rhodium oxide. they may react with the aluminum to get the pure radium, and the radium may have the half-life is larger than 1600 years, then it will become the radon gas. So the first time people get the pure radium, so the Dr. Murray Curie got the pure radium from the barium sulfate. So because of his operation, she got the Nobel Prize in 1911. So the radium in the real life application, so the radium had been used for the commercial things such as the toys I show over here or the needle over here. So, but people in the future research, people found the radium may hurt people's health and it's very dangerous. So they may not use that in the later life. But in today, the radium-223 can also used for treating the cancer, especially in the bones. So we may see the graph over here. The radium rays may break the hydrogen bond in the DNA, and the cancer cell will die